Hello, hello. So today we are talking about significance testing. And we've been talking about the parts of a significance test, but today we are going to be pulling all the parts together to conduct a full significance test. So this is section 9.2 in your textbook. All your book problems for this unit are there, as well as extra examples. So let's dive in to significance tests. So you've seen this slide before. We've talked about significance tests, and we say that they look for evidence against a claim rather than in favor of one. And we went through the whole process of type 1 and type 2 errors about looking for evidence against, meaning we're trying to prove the claim guilty instead of proving it innocent. We can prove it guilty or not guilty. So in order to disprove a claim, we need to create these hypotheses. We have the null, or the HO, and the alternative, the HA. So these are my two hypotheses, and we said that these hypotheses, along with the population and the parameter, are part of the state step. We said these are the state step of my state plan include. So how we conduct a significance test are these same four steps. State plan do conclude. They're the same steps for every test. So we have done 3 different types of confidence intervals. We're going to end up doing 3 more types of confidence intervals, and we're going to do probably 5 or 6 different significance tests. So we have a lot of different tests and intervals that we can do, but it's these same 4 steps every time. So we're really familiar with this state step, population, parameter, and write your 2 hypotheses. So that's state. We've had a lot of practice with that. The plan step is just verifying those conditions, which are random, normal, and then independent. And these 3 conditions are the exact same as with confidence intervals, and we'll go through an example in a minute. The do step, or step 3, this is the one that's different for each interval. This is where we start to see differences in step 3. So step 3 is when I show my substitution into the formula and I calculate my p-value. So we're going to go through what this means, but make sure you get down these parts of step 3. It's substitution into a formula, and we find the p-value. Those are the 3 parts we need in the do step. And then we conclude. We bring it back together. This is the interpreting p-value video. So we're going to go over this again, but for the conclude, we've already talked about it in interpreting the p-value. So these are my 4 steps. Let's put them into a problem. So example 1, and we have 1 example today, says 11% of the products produced by an industrial process over the past several months have failed to conform to specifications. The company modified the process in an attempt to reduce the rate of nonconformities. A random sample of 300 items from a trial run, of 300 items from a trial run, the modified process produced 16 nonconforming items. So if I think about this problem before I do anything, I'm going to annotate some important pieces. The first piece is 11%. This is going to be P. So P equals 0.11. This is my starting value. It says we started with 11% of the products failing to meet conformities or being nonconformities. We're looking to reduce the rate. So we started with 11%. We're trying to reduce the rate. And then we end up taking a sample. And from the sample, we get 16 out of the 300 are nonconforming items. So even though this is a huge kind of wordy paragraph, these are the 3 pieces that are important. The starting value of 11%, the fact that we want to reduce the rate, and then what my sample gave us. So part A of this two-part problem says, do these results provide convincing evidence that the modification is effective? Well, if I just look and I say, well, P equals 0.11 and P hat, or my sample proportion, is 16 over 300, well, that gives me 0.053. Well, 0.053 is lower than 0.11. Can I just say yes and stop? No, I actually can't just stop. Even if it only asks for a significance test, it said do a test of significance, I can't just find P hat and P and say, yay, it's better, or no, it's not better. I have to do all 4 steps. So even if it looks like it's better, we saw P hat was less than P, I still have to do all 4 steps to prove my claim. So if we start at step 1, the population would be the who. Well, the who is the products that we're producing at this industrial process. So you can just say all products, and it knows that that shows me that it's the products, not people or the company. It's just the products that are being produced. The parameter would be, we want to know what percent are non-conforming items. So we're looking at how many items are non-conforming, so we want to test the percent of non-conforming items. So we're trying to figure out how many of these items that are produced are not going to be conforming. We started with the 11%, and we're trying to reduce that number. So the null hypothesis is that we're still at the 11%, that the true proportion equals 0.11, and the alternative is what we want to have happen. We want to reduce the rate, so our alternative is that P is less than 0.11. We also would find this alternative because my sample proportion was less than 11%, so I think it's actually being reduced. Step 2 is my plan step. If I go through the random, normal, and independent, first one, random, it tells me it was a random sample of 300, so I can just say that that was stated in the problem and give myself a check mark. Normal is NP greater than or equal to 10 and N times 1 minus P greater than or equal to 10. So this is the same way of checking normality as with confidence intervals and as with sampling distributions. This normal condition is what we use for proportions. Well, N is 300, P is 0.11, and we want that to be greater than or equal to 10, and we want 300 times 1 minus 0.11 to be greater than or equal to 10. And when I do the calculations, I get that 33 is greater than or equal to 10, check, and 267 is greater than or equal to 10. So the normal condition checks. Both of those are met. Remember, it's an and statement, this and that. Independence is that capital N is greater than or equal to 10 times lowercase n, or the population is at least 10 times larger than the sample. Well, we can assume, I'm going to move this over here, so n greater than or equal to 10 times lowercase n. We can assume that there's more than 10 times 300 products being produced by this machine, or that n is greater than or equal to 3,000 products. So these are my 3 conditions, the same 3 that we've been checking. And that takes us to key point number 1. For proportions, we check the normal condition by using these two equations, not the central limit theorem. Central limit theorem's only for means. For proportions, this is how we check normality. So if we think about the goal of significance testing, I've done the state and the plan step. I'm on step 3, and if I think about what I want to achieve, I want to achieve finding the probability or finding the p-value. So the goal is to find a z-score or to find a critical value, and then from that mark, find the probability or the area under the curve. So if this is my goal, I need to figure out how do I get this z value. And this is where the formula is going to be different for every test. So if we think about this step 3, this do step, make sure you get this down. We are doing a 1 proportion z-test. A 1 proportion z-test because I'm given 1 sample proportion. The formula for a 1 proportion z-test is this formula right here, and in fact, we've seen this already this year. We've seen this exact formula. Now, we're just putting it into the third piece of our puzzle or the third piece of our process. So just to rewrite, P we said was 0.11, P hat we said was 16 over 300 or 0.053, and N was 300. So if I plug these pieces into my puzzle or into my formula, I get Z equals 0.053 minus 0.11 over the big square root of 0.11 times 1 minus 0.11 over 300. And when I do that arithmetic, I end up getting negative 0.057 as the numerator and 0.018 is the denominator. So make sure you pause this video and keep doing this until you get these numbers. So if you type this in and you get something different, retype it, doing the top part first with parentheses, then the division, and then the square root of that answer. So you're going to end up getting these, and then when you do that division, you're going to get negative 3.1666666 or 17. So this is my z-score, and if we think back to that goal, we use the z-score to find the p-value. So this is my z-score equation for proportions. This is my critical value equation. I plugged my numbers in. I got this z value, and now we are going to use my normal curve and say 0, 1, 2, 3, negative 1, negative 2, negative 3. Well, negative 3.17 would be right around here. I'm reducing the rate, so I'm shading below. And if I go to my table A, or my z-score table, you get the area down here to be 0.0008. So there's a very unlikely probability that I'm going to end up getting this z-score, or I'm going to end up getting this sample if the true proportion is still 11%. This area is so small, it's very unlikely to see this outcome if the null hypothesis were true, or if it were still 11%. So before we go to the conclude step, we're going to stop at key point number 2. Make sure you get this formula down. This is the formula we use for the one proportion z-test, or if I'm given one sample proportion in my problem, from this formula, I use table A to find the p-value. Which brings us to step 4, the conclude step. So stop this video and write this down because this is a super important template. So pause, write that down. Okay, now that you have that down, let's break this formula down a bit. It says, since the p-value is less than alpha, my p-value is 0.0008, and that's less than 0.05. Remember, alpha was 0.05. That was from the beginning. Well, if the p-value is less than alpha, I get to reject the null hypothesis that the true, well, we think about the null hypothesis, it was HO, said that P was equal to 0.11. So I get to reject that claim. So if I put that in context, I can say we reject the null hypothesis claim that the true proportion of non-conforming items is equal to 11%. So if we reread that with our pieces, it says since the p-value is less than alpha, so I compare what I got for the p-value with the alpha level given to me in the problem. So since the p-value is less than that, I can reject the null hypothesis claim that the true proportion of non-conforming items, so kind of restate the parameter, is equal to 11%. My p-value is so small, that probability of getting this outcome is so unlikely if this is true, if the null hypothesis is true, that I can reject the idea that the true proportion still equals 11%. If you want to write this kind of in parentheses below, you can't say this kind of out loud, but you can say it in your mind. We believe the alternative is true. And the alternative is that the proportion is less than 11%. So we believe that the alternative is true because my p-value is so small. I can't say that I accept the alternative. I can just reject the null. So it's a lot of wording, but that is how we interpret the p-value. So since the p-value is less than alpha, or is less than or greater than, I should say, so we compare the p-value to alpha, and then we give the p-value and alpha. We can reject or fail to reject the null hypothesis that the true restate parameter to the proportion or mean given to you in the problem. So this is my template. It's this same template every time. So make sure that you write this down and that we keep using this language in this format. So since the p-value is less than or greater than alpha, you write the p-value, how it compares to alpha. We can reject or fail to reject, depending on which of those it is. Remember, less than, reject, greater than, fail to reject. The null hypothesis claim that the true kind of restate the parameter, true mean, true proportion, is equal to the starting value of p or mu. So if it wants you to explain what the p-value of your test means in context, meaning if I want to break down the p-value being equal to 0.0008, that means there's a 0.08% chance, or probability, think probability p-value, 0.08% chance of having a sample or a statistic as small or smaller than the one we got from the sample. So there's only a 0.08% chance of getting this sample if the true proportion of all products is 11%. And this part we broke down in the interpreting p-value video. So this could be like a part B. It's taking the p-value and then rewriting it in context. And this is kind of the template that it's looking for you to explain the p-value. So there's two templates we've been given. One for how we state the p-value, and then the other is putting it back in context of the problem. So that's a wrap. I know that was a lot of words and processes, but it's piecing together everything we've been doing. So we use the 4-part process to conduct a significance test, and the p-value is always interpreted in context and compared with the level of significance, or alpha. Once again, this is section 9.2 of your textbook. Please go there for more examples and extra practice. I'll see you next time.